Hello everyone, this is Songyang Zhang from University of Rochester, and now I present our paper, Learning a Grammar Inducer from Massive Uncurated Instructional Videos. This work was done during my internship at Tencent, collaborating with Linfeng Song, Lifeng Jin, Haitao Mei, Kunxu Dongyu, and Jiebo Luo. Grammar induction aims to find hierarchical syntactic structures from plain sentences. Many efforts have been made in supervised grammar induction. Basically, they ask human experts to manually annotate the constituency trees and design a model to learn from the annotated trees. However, the problem is also very obvious. It has two limitations. First, annotating syntactic trees by human language experts is expensive, cumbersome, and time-consuming. Second, these datasets are limited to news-aware domain in several major languages. For many minor languages, there are no such annotated datasets. Sometimes we cannot find enough human language experts for annotating. To mitigate this issue, many recent approaches focus on unsupervised grammar induction. It aims to learn from large-scale unlabeled text. The advantage of these approaches is that the text data is of large scale. The disadvantage is that we do not have annotations. On the other side, unsupervised grammar induction can also provide evidence for statistical learning of grammars, because it has minimal assumptions about the linguistic knowledge built into the models and succeed in inducing accurate grammars. Recent approaches find that images can help unsupervised grammar induction. The intuition here is to exploit the regularities between text spans and images. However, when we compare with a verb phrase such as jump and stomp, static images do not contain such dynamic change or object. Therefore, images may not benefit verb phrases. Our earlier work shows that using video can further improve the grammar induction methods. Videos include not only static objects but also actions and state changes useful for inducing verb phrases. However, both image-aided and video-aided grammar induction still suffers from data limitations. A typical dataset collection pipeline looks like this. They first collect images or videos and then ask annotators to describe them. Since the pipeline requires human efforts to describe images or sentences, it is harder to scale to larger size. Meanwhile, this pipeline assumes the meaning of a sentence needs to be identical to the corresponding image or video. This assumption cannot reflect the ambiguous correspondence between language and the real-world context in language acquisition. Due to the aforementioned limitations, we are interested in two questions. The first question is, how would a grammar inducer perform when it is trained only on noisy multimedia data? Second question is, how would the scale of training data affect the performance and cross-domain robustness? The instructional video on YouTube provides us a good platform to answer our question. As shown in this example, instructional videos usually have a narrator talking about what they are doing. The video and the sentence may not well align, but it could reflect language acquisition in the real world. Meanwhile, such dataset collection does not require any human efforts and thus scalable to any sizes. Before going deeper into our model, I will first introduce the background knowledge that we will use in the following parts. Our work is motivated by compound PCFG proposed in SAL 19. 1 year later, visually grounded compound PCFG is proposed in EMNLP 20. Visually grounded compound PCFG extends the compound PCFG by additionally considering an image sentence matching loss during training. Later on, multimodal compound PCFG is proposed in NACO 21. The MMC-PCFG further extends the compound PCFG by additionally considering a video sentence matching loss during training. Now let's go through our methods. Given a YouTube video, we would like to generate a set of video and subtitle pairs where each subtitle is a complete sentence and is aligned in time with its paired video clip. But our observation finds that most obtained subtitles are not complete sentences. In order to find each complete sentence and its paired video, we design an algorithm with two steps shown here. The first step is sentence segmentation. The goal is to find the complete sentence from subtitles. We first concatenate all subtitles into a long sentence and use a punctuation restoration model to insert punctuation and segment sentences based on certain punctuation. The next step is video clip extraction. The goal is to trim the corresponding video clip for each processed sentence. We assume each word within the row subtitle occupies equal time and record the start and end time for each word. Then we compute the start and end time of each sentence and trim the video clip based on sentences start and end time. After collecting sentence and video pairs, the next step is to build a strong grammar induction model that can benefit from them. As shown in the left part of this figure, the PTC-PCFG model composes of a video encoder, a span encoder, and a parsing model. Both the video encoder and span encoder are initialized from the EMNLP model. It is a pre-trained video text matching model, and it is simple in design and shows superior zero-shot performance on many video understanding tasks, such as video retrieval, video question answering, and so on. And now let's introduce each part. The first step is to encode a video B into its representation. To do this, we first segment video into several video clips and extract their features with EMNLP model. And we use the average feature as its representation. The next step is to compute a span representation C for each particular span in a sentence. The pre-trained text encoder consists of a word embedding layer and two stacked fully connected layers. Following previous work, we expect to learn multiple different span representation, and each is specified for one non-terminal node. However, directly applying the pre-trained text encoder is not feasible since it has only one output layer. Therefore, we duplicate the last fully connected layer multiple times, and each of them corresponds to a non-terminal node. In more details, we first encode each word with a word embedding, and then feed the word embedding to the ReLU maximum polling and each label-specific output layer. The span representation C is the sum of all label-specific span representation weighted by the probabilities we predicted here. During training, we optimize both the video text matching loss and evidence lower bound. We first compute the similarity between a video clip and a particular span via dot product, and then compute a hinge loss. The epsilon is a positive margin, V prime is a clip feature from different video, and C prime is a span representation from different sentence. The video text matching loss is correspondingly defined here. P is a probability of a particular span C being a syntactic phrase. Finally, the overall loss is computed by the elbow and the video text matching loss, and alpha here is a constant balancing these two terms. During inference, given a sentence sigma, we predict the most likely tree without accessing video, as shown in the right figure, and we predict the most likely tree with the CYK algorithm. Following previous work, we evaluate all systems on three benchmarks, DDEMO, UQ2, and MSRVTT. Instead of training on benchmark datasets, our models are trained on data collected from 100 million datasets. In our evaluation, we follow previous settings, such as discard punctuation, lowercase all words, and so on. All models are trained 5 times for one epoch with different random seeds. And we use the average sentence level F1 and the corpus level F1 as metrics. And since testing dataset does not have annotated trees, we use a state-of-the-art constituency parser to predict the reference trees. We first evaluate the robustness of our models across different datasets. We evaluated the previous state-of-the-art method MMC-PCFG trained on DDEMO, colored by red, MMC-PCFG trained on UQ2, colored by yellow, and MMC-PCFG trained on MSRVTT, colored by green. Each model is evaluated on 3 testing sets. We can observe that MMC-PCFG trained on MSRVTT achieves the best overall performance, while MMC-PCFG trained on UQ2 is the worst. We believe this is due to the different number of training instances and the domain gap between different datasets. We then train a model on a subset from hot 100 million, and we can find it is the best or the second place regarding SF1. This demonstrates that our proposed video text training instances are abundant, rich in content, and can serve for general purpose. Next, we train PTC-PCFG on the same subset of the hot 200 million. We can observe that PTC-PCFG outperforms MMC-PCFG in SF1 metrics. This demonstrates that our model can leverage pre-trained video text matching knowledge and learn consistent grammar induction. We also compare CPCFG, MMC-PCFG, and PTC-PCFG trained on hot 200 million over a different data scale. On DDEMO and MSRVTT, we observe that PTC-PCFG achieves the best performance at a certain point, and further increasing the number of training instances does not improve the performance. In contrast, the performance gain of PTC-PCFG on UQ2 can be further increased with increasing training data. The reason can be that the domain of hot 200 million is closer to UQ2 than the other 2 datasets. In this figure, we visualize a parsing tree predicted by the best run of different models trained on different datasets. The red line shows a difference between predicted trees and the reference trees. And clearly, we can see that our PTC-PCFG can leverage the pre-training matching knowledge and make the correct prediction. In conclusion, we find that massive instructional in YouTube video and subtitle pairs can improve grammar induction. We also find that a multimodal pre-training model can be leveraged to learn better video span correlation. In the future, we would like to explore more models and more public available data. Our code is released here. Thanks for listening.